Esta charla estará a cargo del Dr. Robert Steele. Él pertenece al Servicio Geológico de los Estados Unidos. Esta presentación cabe resaltar que se realizará en el idioma de inglés.
Gracias. Buenos días. Yeah, that's fine. I'm happy to be here. I was invited down to work with the environmental and hydrogeology groups to help them with some of their abandoned mine land studies. So what I'd like to do today is describe some of the abandoned mine studies that I've done in the United States and explain some of the experiences and the lessons that we've learned working in some copper deposits in the northeastern United States in the state of Vermont. The deposits I'll be talking about are what's called the Vermont Copper Belt, which is in the eastern part of the state, which I mentioned is in the northeastern United States. There are three deposits there: the Elizabeth Mine, the Ely Mine, and the Pike Hill Mine. Relatively speaking, these are fairly small deposits. The Elizabeth Mine was the largest. It mined roughly 3 million tons. The Ely Mine produced about 500,000 tons of ore. And the Pike Hill Mine produced only 100,000 tons of ore. And you can see that the ore grades were on the order of 1.8 to 3.5% with a little bit of zinc. These deposits formed on the ancient seafloor. They were massive sulfide deposits, meaning that the ores were dominated by the sulfide mineral pyrite, which means that these ores have a lot of potential to generate acid. The ores were hosted by metamorphosed shales, marbles, and amphibolites. So the rocks have a little bit of acid neutralizing potential in the carbonates, but not a lot. And then the mines were in operation intermittently from 1809 to 1958. I'll mostly talk about the Elizabeth Mine and discuss a little bit about the Pike Hill Mine today. This is just a diagram showing some leaching test results that we did on various types of ore and waste rock and mill tailings at 3 different mines. What I've plotted here is copper concentration versus pH. And you can see that these rocks are basically classic acid mine drainage sorts of waste materials. You see very low pHs and high concentrations of copper and other metals coming out of these waste materials. As far as the history of the Elizabeth Mine, it was first discovered in 1793, and its early production was for copperas, which is basically ferrous sulfate. It's a compound that was used a lot previously for disinfectants, dyeing leathers, and other uses. It's since been replaced by many other compounds today. But this is the prime commodity that was targeted early on. This is a photograph from the 1800s that shows the Copper's factory at the site. Later in the history of the mine, they started producing copper ores through roasting and copper smelting on site. The mine was dormant for a number of years, and then in the World War II era, they reopened it using more modern mining techniques. Interestingly, the way that they produced the copperas was very similar to what was done back in the 1500s, is displayed in Agricola's famous book De Re Metallica, where basically the ores, in the case of Elizabeth, pyrrhotite-rich ores would be roasted over fires. The leachates coming from these piles would then be taken into evaporation vats, where the main process to produce copperas or melanorite was simply evaporation. And they would put sticks, twigs, other material in the vats to provide a substrate for crystallization. This essentially was the same process that was used at the Elizabeth Mine in the 1800s. This is an overview of the site. The area of the ancient copper workings is on this side, in this area right here. The modern waste, or the more modern waste from the World War II mine areas, is tailings pile here. There's also a pit lake on the site that was also part of the mine production, but most of the production came from underground workings. It started approximately in this area and trended north underneath the river that is impacted by the Elizabeth mine. So if you look at the parts, there's tailings pile 3, which is actually a waste rock pile. These were the waste from the older style of mining. So these were hand-sorted ores, big cobbles of sulfide-bearing rocks on this landscape. It was designed so that it both oxidize the sulfides and drain well. Tailings pile 1 and 2 are the more modern era mine waste shown here. The pit lake is here, as I mentioned before. Underground workings, the waste rock, and then finally the tailings. So even though all of these materials, both the wall rock and the unmined ore here and underground, the waste rock and the tailings pile, these all essentially have the same mineralogy. Quartz, muscovite, cementolite, a little bit of calcite, pyrrhotite, and trace amounts of chalcopyrite and sphalerite. Even though they're similar, the way they evolve mine drainage is quite different because of the nature of these different settings. Again, this is just a picture of the different solid waste types. We have these waste rocks, very coarse waste rock piles, and then the finer grained tailings shown here during the beginning of the mine cleanup where they were trying to grade back the front of the waste pile. As far as the environments go, we have 4 different end members. This is a cross-section of the mine workings, looking from south to north. So this is the beginning of the mine workings showing the mine stopes. It's filled by water at approximately this level, and then right on the banks of the river, shown right here, the mine waters will discharge from this small vent structure right on the riverbanks. So if you look at the mine working waters, we have the pit lake, which has good access to oxygen because it's a lake at the surface. We have these underground workings where oxygen is rapidly consumed so that the waters leave the mine workings on the riverbank where they lack oxygen. And so these are areas that are dominated water, whereas the reactive surface is much less because they're just looking at mine walls. In contrast, we have the waste rock piles that have good access to oxygen because of their coarse grain size, and they have a lot of reactive surfaces because the material's been crushed. And then the other type of waste are the mill tailings, where there's a lot of reactive surfaces. Mill tailings were crushed to very fine grain size, the size of sand or silt, but because of the fine grain size, the piles tend to stay saturated with water so that oxygen is consumed, so the waters emerging from the base of these are lack oxygen. So we have two water-dominated systems, one that's oxic, one that's anoxic, 2 rock-dominated systems with a lot of reactive surfaces, one that's oxic because of the porosity, and one that's anoxic because of the lower porosity. So together, these 4 different end members produce different styles of water because of these differences. So again, to summarize these environments, I just did that, but the oxic mine wastes, the waste rock, low water rock ratio, and a good supply of oxygen. The tailings, as I mentioned, low water rock ratio, but a limited supply of oxygen. The pit lake has a high water to rock ratio because the reactive surfaces are just pit walls. And then there's a good supply of oxygen because it's a lake at the surface. Whereas the underground mine pool also has a high water rock ratio, but oxygen is limited because the waters are flowing through extensive mine workings. So when we look, for example, at mine drainage from these different end members, here we're looking at iron versus pH. When we start with the waste rock piles that were oxygenated, these are the worst water quality samples that we see on site. They have low pH, and they have high iron and other total dissolved solids. In contrast, when you look at the waters emerging from the tailings pile, you'll see equally high concentrations of iron, but the pH will be much higher. The reason for this is that these waters are dominated by ferric iron, Fe3+, which has low solubility, as shown by this line here, whereas these waters are dominated by ferrous iron, Fe2+, which has a much higher solubility. The reason that all this iron is Fe2+ is because the water table in the tailings pile is high, and the oxygen gets stripped out early on by oxidation of sulfides, so that the iron, when it's dissolved, is ferrous iron, which is more soluble. Now, when we look at the mine workings, the underground mine workings shown here are intermediate in the iron concentration and pH. Again, this is a reflection of the fact that most of the iron in the underground workings that are emerging at the riverbank are dominated by ferrous iron, whereas when you look at the pit lake, where there's lots of oxygen, its waters are shown right here, so it's dominantly Fe3+, but the concentration is lower because the reactive surfaces are much less because we just have rock faces available. You see similar sorts of trends when you look at dissolved sulfate, the other part of acid mine drainage. Okay, there's two contrasts. But when you look at sulfate, you see similar sorts of relationships in that the waste rock piles have the worst, lowest pH, highest sulfate concentration. You see similar high concentrations at a higher pH for the waters coming out of the tailings piles. And then when you look at the underground workings, it's again intermediate, and again the pit lakes sort of follow along the same trend as the worst acid mine drainage. And for reference, I have some background waters from unimpacted streams shown as well. Copper is a little bit different in that all of the data follow along a similar sort of trend, but part of the reason for this is that there's a number of reactions that can keep copper from going into solution in these tailings piles of water that are kind of unique to that setting. At the upper weathering surface, there are sorption reactions where the copper can be removed from the solutions by ferric hydroxide minerals, secondary ferric hydroxide minerals that form. The copper can also replace the pyrrhotite as the waters flow through the tailings pile as well. So there's two different processes that can contribute to these lower copper concentrations here. Okay. One of the other specific studies that we had to do at the site, or EPA, the Environmental Protection Agency wanted us to do, is to add greater insight into the geochemistry of the pit lakes. So we conducted a study that looked at the pit lake water quality over the course of a year. One of the things that we were interested in was looking at the thermal or temperature structure of the lake. To do that, we deployed buoys that had temperature sensors at various depths within the lake so that we could map out temperature variations and the thermal structure of the lake throughout the year. For example, we started in the summer months, and we see that the shallowest waters had the warmest temperatures, whereas the bottom waters in the lake had the coolest temperatures. But in the early fall, we saw that the lake water overturned and mixed. So basically so we had constant temperature at all different depths in the lake until the winter time when the lake freezed over, as you can see, or froze over, as you can see right here. And here we had an inversion of the temperature structure where the lowest waters had the highest temperatures and shallowest waters right beneath the ice had the coldest temperatures. The reason for this is that the lake has a sloping bottom, and we think that contaminated waters were flowing down the gravel bottom of the pit lake and flowing in at the bottom, presumably year-round, but you could only really notice it in the winter when you didn't have wind mixing at the top of the lake. Whereas for the ice-free parts of the lake, wind mixing was enough to sort of mix the water column. We get support for this idea when we look at depth profiles throughout the lake. Here, depth is plotted against pH, depth, specific conductance, which is a measure of the total dissolved solids, and here, depth is a function of the concentration of dissolved oxygen. When you look at all of the sampling except for, the summer samplings show variation in pH. depth. The only time where we saw any sort of variation was when the lake started to freeze over. We could start to see a hint of lower pH at the bottom. It was completely frozen over just before springing up. We saw distinct stratification. Again, this is a reflection of these concentrated waters flowing in at the bottom of the lake that were going most of the year when the lake was ice-free. There was enough wind mixing to keep a homogeneous profile. You only saw this stratification when the lake was iced over. Same thing when you look at total dissolved solids. You can see only a hint of the stratification showing up in the winter and early spring months. And the same idea is shown up in the dissolved oxygen profiles. Very little change, except when you see an ice cover. And the fact that you see lower dissolved oxygen concentrations suggests that you do have these ferrous iron solutions entering the lake at the bottom under these stratified conditions that are consuming the oxygen. Another interesting aspect of these pit waters, that you'll recall the different profiles or the different environments produce a different pH range. So when you look at mine drainage composition of copper versus zinc, you can see that the lowest pH waters had a very characteristic copper to zinc ratio ranging between 10 to 1 and 1 to 1. That would be all of these points right here. Whereas when you look at the waters that had higher pH, you'll remember that the mine workings had an intermediate pH, and then the tailings water had an even higher pH. You see that the copper to zinc ratio of these decreases where they're dominated by zinc instead of copper. A likely explanation for this is shown in this slide. This slide shows the ability of dissolved metals to absorb iron hydroxides as a function of pH. So basically, it's the percent sorbed plotted against pH, so that at lowest pH, this diagram basically tells us that all of these elements will be in solution. There will be nothing absorbed onto the solids. Whereas when you go up in pH, you can see how over the course of 1 to 1.5 pH units, these metals will be removed effectively by these iron hydroxides. But you'll also notice that the pH where these curves start is different depending upon the metals. So when we look at the pH ranges that we saw with our water samples in these different environments, we saw that the most acidic waters had pHs between 2.5 and 3, and we see that that's a pH range where you would expect the copper and zinc all to be in solution. And basically that's what we saw in the other diagram. When you go and look at the pit lake, again, it had an acidic pH ranging from 3.5 to 4. But again, these are conditions where you would expect all of the metals to be in solution and none of the copper and none of the zinc to be absorbed onto the ferric hydroxides. In contrast, when we look at the tailings waters, coming out of the bottom of tailings, well actually no, when we look at the mine pool emerging on the riverbank first, we see that it had a pH between 4.5 and 5.5. But if you look at this pH range, you see that that's in a range where a majority, but not all the copper should be removed, whereas very little of the zinc would be removed. So this is the first water samples where we start to see this change in copper-zinc ratio in the mine drainage. And then when you look at the water coming out of the tailings piles, you see a higher pH, ranging from 6 to almost 7. And here you see that these are conditions in which most of the copper should be removed and intermediate amount of the zinc. So basically this sort of sorption model seems to explain well the pH differences and how that relates to the copper-zinc ratio of mine drainage. So these sorts of insights will be very useful for designing treatment for the mine site. There are many in the United, well, not many, but there's some people that think that abandoned mines can clean themselves up on their own if given enough time. So I decided to try to see if I could figure out, with some simple calculations, how long it would take the oxidation of sulfides in this tailings pile to dissolve away and solve itself. So we had estimates of the total pyrrhotite content of the tailings pile. So I said, how much sulfate would that pyrrhotite produce? And that's this amount up here. So 815 million kilograms of sulfate. With the studies that we did here, we were monitoring the chemistry over the course of the year on Copper's Brook downstream of the tailings piles. Throughout much of the year, well, throughout the winter, spring, and early summer, Copper's Brook was flowing from the waste rock piles down through here and flowing to the river along here. But the Copper's Brook at this point was also receiving discharges from the tailings pile. However, in the summer, the upper watershed was completely dry, so that all the water being delivered from the tailings, or to Copper's Brook in the river, was only coming from the tailings discharge here. So from our Copper's Brook data set, I show sulfate load as a function of time. These are the months, October, November, well, starting with October and ending up in September of the following year. So that in the spring and winter, this is the combined discharge that we saw at the bottom. But you'll notice that in the summer months, when the upper watershed was dry, it was a pretty constant discharge of sulfate. This was sulfate that we knew was only coming from the tailings piles. So basically, we could use these months here to calculate what the month of discharge of sulfate coming from the tailings pile alone would be, and that number would be 21,000 kilograms per month. So if you take the number of the total amount of sulfate that you could potentially produce from the tailings pile, divided by the rate that we know we are losing per month, you can calculate how long it would take to weather the tailings pile away on its own. That number is just a very short 3,000 years. So clearly, as far as abandoned mine cleanup, letting nature take care of its problems is not a viable option. We need to do something to, speed up the cleanup process. So as far as what they've decided, my work up at the Elizabeth mine began in 1998, so a lot has happened in the meantime. EPA has started their cleanup work there and is actually now pretty close to being finished. But ideas, well, what they were trying to do for the waste rock piles, first was to try to stabilize the tailings piles. The front slope of it initially was very steep. There was a lot of concern that it could fail and impact and have like mass wasting impact in the river downstream. So they wanted to stabilize that. They also wanted to take the upper waste rock piles, which run a very steep slope. Very little could be done on site for that. So they wanted to remove all that material, put it on top of a tailings pile, and then cover the whole thing to keep it isolated from rain and other sorts of moisture. And then the idea was that once they covered the waste rock in the tailings pile, eventually the tailings pile would dry out to very low base flow composition, at which point they might assess long-term passive treatment of mine drainage at that point. But when they started this project, they had an unforeseen incident happen with the water chemistry that I'll explain next. This is a cross-section of the tailings pile. There were two parts of it. So in the initial reclamation plan, they wanted to grade back the surface on both the lower pile and the upper pile. They built a stone buttress at the bottom with a drain system that would add stability to the bottom of the pile to prevent it from failing. And then they were also going to put a plastic cover over the top to isolate it from rain and snow. Diversion channels up above to divert surface water flow away from this, and then a vegetated cover of about 1 meter of soil and vegetation above. That was the plan. So they started construction on this. As you can see right here, they've started grading and revegetating this front surface. They built their drain system here. There were some original horizontal drains that went into the tailings pile initially. They drilled some new ones to help drain the pile better. And then they also put in a drain system just for this front face. then a series of settling ponds here. They constructed better channels for the seepage from these drains shown here. And all this before it exits down Copper's Brook to the receiving river. So surface water diversion I mentioned. There was existing horizontal drains, they added more, they put in these features called toe drains, then the sediment basins. But, and this is just a close-up of some of the construction work that they did, the channelized flow going down to the sediment basins. So before EPA started working at the site, this is what Copper's Brook looked like when it was coming down the valley from all the mine sites that we discussed. You can see it mixing with the Pompanoosuk River. You can see a lot of precipitation as the acid mine drainage mixes. And you see from this diagram taken from across the river how the contamination tended to just hug the far riverbank. So there was some mixing, but it didn't go very far across the channel, at least right here at the confluence between Copper's Brook and the Pompanoosuk River. Shortly after they did their construction, this is what it looked like from the air. Here's Copper's Brook, here's the Pompanoosuk River, but you see that suddenly there's a lot of iron precipitate and it basically reaches from bank to bank, right as soon as it mixes. So obviously the local communities were concerned. EPA didn't understand what was going on. So we tried to help them figure it out. And if you look at the drainage coming out of the mine, this is what you would see. This is either iron load versus time from January 2005 to September of 2008. Here's the flow coming out of the watershed, so you can see that it didn't change very much. The orange is the load coming out of the horizontal drain systems that were originally there and the one that they added. You can see that over this time period, that didn't vary much. But when you look at the toe drains, those new drain systems that they installed right at the face of the tailings pile, you can see that it had a big spike over this time period in iron concentration, which explained the greatly increased iron load coming out of the system. Basically, the iron load went from slightly below 300 pounds per day, increased almost 3 times to close to 900 pounds per day. So basically what was happening was coming out the toe drains, a feature that was right at that front face of the tailings pile. So again, we have this diagram, but observations that they made at about the same time was that the water table initially at the top was near the top of the tailings pile and dropped down to near the base of the tailings pile before construction started, but they noticed right after construction or shortly after, the water table at the front actually jumped up close to between 5 and 10 meters, which coincided with this big iron problem that they had. So to explain that, this is data from a different study, but I think it illustrates what happened very well. This is a cross-section to a tailings pile in Canada, one that's full of sulfides, much like the Elizabeth mine. You can see the water table shown here, and you see a lot of chemistry, EH, sulfate concentration, iron, and pH. But the point to get from this is that when you look at the vadose zone waters, the poor waters in the tailings pile above the water table, you see that you get much higher concentrations of iron, lower pH, higher sulfate. So basically what I think happened is that once that water table jumped up, you suddenly wetted a lot of these high concentration vadose zone waters, and that started flushing through the system. So that's where you saw this high iron concentration coming out of the tailings pile. And then the reason why you saw that dramatic effect in the river can be explained from this diagram. Where what this diagram looks at, it looks at the rate of the oxidation of ferrous iron, which is very soluble, to ferric iron, which is insoluble, as a function of half-life plotted as pH, as shown by this curve. When you look at Copper's Brook and some of the co-drain waters, you see that they have low pHs. So if we look at low pH conditions, the oxidation rate of ferrous iron to ferric iron that you precipitate is very slow. It would take a year or more to do that oxidation. But when you take these sorts of waters and mix them into the river, which has a pH of 8 to 8.5, you can see that the amount of time to oxidize that iron is very short, much less than an hour. So basically it's these mixing of these acidic waters with this high pH waters that cause this dramatic, immediate iron precipitation event, which caused all the, the dramatic effect that we saw in the river. So as we saw, that iron load has since moved through. We did hydrologic calculations about travel times of water based on the known permeability. And it all makes sense that all those effects were right at that front part of the tailings pile where they built the butters and the water table jumped up. So basically, to deal with this, EPA had to respond quickly. So they built this active treatment plant at the base of the tailings pile, and which is shown here. It's only run from the spring to the fall. Everything is frozen in the wintertime. And basically what they're doing, they're neutralizing the mine drainage by adding hydrated lime, calcium hydroxide, which is added here. It then goes into this rotating drum where the waters are mixed, and then it's then just discharged out to the settling pond. And this has done a very effective job at removing iron and sulfate. And now presently, the poor waters in the tailings pile are draining down to what they hope will be base flow conditions. So now EPA is trying to consider some deactivating the active treatment plant because it's very expensive to operate. It requires staff, it requires electricity. To go to something that's more passive, that would be less expensive in the long term, but just as effective. So when you look at the site today, this is what it looks like. The piles have been regraded, revegetation. The upper waste piles have all been stripped, put on top of the pile, which is underneath the cover now. They're collecting water here, pumping it up to the treatment system, and then discharging it downstream. So the river has recovered a lot. But now they're trying to plan what they're going to do for passive treatment systems. There's a number of options out there, but one of the biggest challenges is here's the river. The amount of land that they have to build a passive treatment system is fairly small. But a good example of a passive treatment that could be effective is treatment with a constructed wetlands. But we've been able to gain some understanding of how wetlands would perform by looking at a natural wetlands at the Pike Hill mine, also in the Vermont Copper Belt. So we're just talking about Elizabeth, but downstream of Pike Hill, there are these natural wetlands. So we did some studies up there to better understand how the biochemistry, geochemistry of wetlands would deal with acid mine drainage. So here's an overview of Pike Hill. The mine's here. It's near the headwaters of the stream. This is what the mine site looks from the air. There's a bunch of waste piles and mine workings that contribute acid mine drainage to a stream that's discharging. We installed a weir at the base of the stream, so this is what it looks like with spring melt. You can see the acid mine drainage and the iron precipitates. We did some monitoring in the stream for over a year at several different sites. We started with the mine drainage input. We had a sample site above this series of wetlands, which falls here, and then we had a downstream site that was conveniently located near the bottom end of the wetlands. So for example, on this diagram, you can see distance downstream and specific conductance or total dissolved solids or pH on this diagram. The reach that includes the wetlands are shown by these boxes here and here, so that you can see as the contaminated stream enters the bigger stream, you get rapid dilution and you get rapid neutralization of pH. And you also notice that in the wetlands, at least as far as these major water quality parameters of pH and specific conductance or total dissolved solids, the wetlands do not seem to be having a big effect. when you look at sulfate concentrations at these 4 sites, you can get a general sense of the role that dilution has in these sites. But when you look at iron, you don't see the same sort of trend. You see a more rapid drop in iron concentrations. It's fairly farther downstream. Again, this is a reflection of those iron precipitation reactions that we saw were so important at the Elizabeth mine. When you look at the loads that are coming downstream, you can look at both the dissolved loads, but also the fine particulate loads, which is what we're doing here. So here I've got loads of iron, copper, and zinc shown for different seasons at the 3 different sites. When we initially started the site, we only had 2 sites and decided that we needed to add that middle one. So for iron, for example, you see the acid mine draining starts off where the dissolved load shown in blue, most of the iron is in the dissolved phase coming out of the mine, and very little is as particulates, which are shown in the red. But by the time you get down into the wetlands, or in this case just before the wetlands, we see that instead the iron load is greatly reduced, but it's mostly in the particulate form. So again, it's these neutralization and precipitation of these fine particulates that are being carried down to the wetlands. When you look at copper loads, you see a very similar story. The copper coming out of the wetlands is dominantly dissolved, but once it gets down into the wetlands or before the wetlands, much more of it is being carried, it's reduced, it's being carried as particulate load. If you think back to those sorption curves, the absorption curve for copper is at a pretty low pH, so that makes sense that copper would be carried on these iron particles. In contrast, when you look at zinc, you see that zinc starts off as mostly dissolved load, but as it gets down to the wetlands, still a large portion of the zinc is still dissolved. When you think back to those sorption curves again, the zinc curve was at a higher pH. So basically, that's consistent with this sorption behavior before where you would expect a lot of the copper to come out on these iron particles that are being carried downstream, whereas you wouldn't expect the same amount of zinc to come out. So to better understand what the wetlands are doing, we went into the wetlands. You can see various pictures of them here. And we took very short sediment cores, like less than a meter, to try to understand what was happening in the subsurface of the wetlands. We also had a portable XRF unit, so we could also map out iron concentrations in the surface sediments of the wetlands. And what was a common feature, particularly in this area, you can see these very fine mine drainage particulates settling out in the upper parts of the wetlands throughout this area where we did the survey. So at least as far as the iron budget goes, there was like, in essence, an oxide facies at the top of the wetlands. But again, we're also interested in what's happening at depth in the wetlands. So in these cores, several cores are plotted here, and again, they're very short, feet, so it's like a meter. But just below the subsurface, where the wetlands became anoxic, in this one core, 3-5, which is located here, we saw this huge spike up to 15 weight percent sulfide sulfur. So these are sulfide minerals that are forming in the subsurface in quite high concentration. In some of the other cores, we saw similar sorts of spikes in sulfide sulfur in the subsurface. Other cores, we did not see that. But then when we x-rayed the sediments here, we found that pyrite, pyrrhotite, chalcopyrite, and sphalerite were actually forming, modern day in the wetlands. When we looked at copper, zinc, and iron profiles, the copper profile showed some similarity to the sulfides as the zinc, but there was some messiness to it. And then the iron profile was a little more confusing to interpret. But you remember, for iron species in these wetlands, at the surface we had a lot of iron as these mine drainage precipitates, whereas at depth it's occurring as sulfides. So there's 2 different sources of iron showing up when we do a bulk analysis of copper in these short cores, and the same thing goes for copper absorbed. To get a better idea of what the wetlands are doing to the sulfate, we can look at these 2 diagrams where, again, looking downstream as shown on the horizontal axis, On this axis, we're simply looking at sulfate concentration. How much is in the water in terms of milligrams per liter? So we see this decreasing trend as you go downstream. However, when you look at that in terms of sulfate load, not only the concentration, but how much water it's dissolved in, when you look at the sites above the wetlands, you see a pretty constant sulfate load that's entering the wetlands, shown schematically by this red line. Whereas when you look at the sample sites that are downstream in the wetlands and below, you also see a pretty constant sulfate load, but it's reduced by about half of what we see in the upper part. So basically what we think is happening here is that there are microorganisms called sulfate-reducing bacteria. What they do, they'll take organic matter and sulfate, and as part of their metabolism, they'll take that sulfate, reduce it to sulfide and bicarbonate as part of their metabolism. So we think sulfate-reducing bacteria what are actively facilitating the removal of metals and sulfide sulfur in the wetlands. So schematically, the way we think this works, here's a cross-section of the wetlands. We have water coming in, water flowing out. We know at the surface we have this oxide zone of iron and this reduced zone. If you look at the EH differences between iron reduction and sulfate reduction, you expect them to be separated in space. So basically lower down in the pile we have this sulfate to sulfide reduction zone. So what we have coming down in the stream, we have these fine particles of iron that have copper absorbed to them. They're entering the wetlands. They're getting transported into the subsurface. But once they get below this ferric iron to ferrous iron boundary, you get reductive dissolution of the particles. They'll dissolve. They'll release ferrous iron, Fe2+. There's two fates to the ferrous iron. Some of it escapes and leaves the wetlands, which we've been able to identify in our water quality sampling. But clearly some of it travels down and ends up getting precipitated as sulfide minerals like pyrite and pyrrhotite. When you look at copper, similar sort of fate, with this dissolution of these particles, you will release copper to solution. Again, some of it will escape, and we've noticed higher copper concentrations in the waters down below, but clearly some of it is going deeper in the system, combining with sulfide and producing copper sulfides. Now, if you worry about what's happening with the sulfur in this system, because we've removed so much iron through neutralization upstream, there's no longer enough metal to consume all of the sulfur that is moving through the system. So that means some of the sulfur, the sulfide sulfur, will combine with the metals, but then some of it also will either be lost as a gaseous phase to the atmosphere, or it could get reoxidized to sulfate and continue downstream. Now what's interesting about this is that when you look at the ore grades that were mined at the Elizabeth mine, the Ely mine, and the Pipe Hill mine, you see copper grades of around 1.8 weight%, zinc around 0.5, copper 3.5, 2.5 at these different mines. When you look at those individual samples in the wetlands of these sulfide minerals that are forming today, you can see that the copper grades that we're seeing forming in the wetlands are basically ore grade compositions. The amount of zinc is quite high, ore grades as well. Iron's high, which we don't have information on the ores, and then the sulfur's quite high as well. So basically what we're doing here is taking mine waste, mobilizing it, and reforming an ore deposit there in the wetlands. So as far as passive treatment, natural or constructed wetlands, not natural ones, could be very effective at both reducing sulfate and metals and mine drainage, say at the Elizabeth mine, when they try to figure out what they're going to do for passive treatment there. So in summary, I tried to show you that the Elizabeth mine, even though you have a very similar starting composition of water, the same mineralogy and all those different mine drainage settings, you did not get the same sort of mine drainage composition in all those settings. Instead, you saw some distinct differences And all these differences are basically related to the availability of oxygen, but also the availability of reactive surfaces, whether it's crushed up waste rock or mill tailings, or just rock faces on mine workings, is what mainly contributed to all those differences. We discussed how when EPA started the remediation, they encountered this unexpected problem with the iron chemistry coming out of the tailings pile. Well, we think we figured that out, and now the site is on a good path to its final eventual cleanup. But the last piece of the puzzle that EPA has to figure out is what are they going to do for long-term passive treatment. And from our work up at the Pike Hill mine, we see that a constructed wetlands beneath the tailings pile may be fairly effective for this long-term passive treatment of mine drainage there. So with that, I'll say thank you and ask for any questions.